Hello guys, welcome to today's lesson, and in today's video we'll be talking about induction, which is the fourth chapter of the second unit. And so let's start. First of all, I'm gonna tell you a little story. So there's a person called Mary who is really old, and she's just lying in her chair one day and she was just resting, and then one of her descendants came up and then asked her, how old is she? And then she is really, really old. So she answered, I am 122 years old. And then, so the kid, who is a kid, is really confused. She's like, you're so old. How do you know your age? So her answer was, because since this year I am 122 years old, this means that last year I was 121 years old. And that is where she got 122 from. And the sort of argument that she is trying to use is called inductive reasoning. If all the elements are present, it can be used in proof by induction, because this applies to every single age. She's saying 121 because she was 120 the year before that, and then all the way to when she knew her age, for instance 14 years old. So then if you miss any sort of step, as you can probably see in this argument, then you invalidate your whole proof. So this is why we need to ensure the precision of proof in mathematics. So in today's lesson, we may come across a particular pattern in the form of a conjecture. A conjecture is a hypothesis that generalizes a pattern. You can test different cases to verify if the conjecture holds. For instance, if we have a sequence which is 2n, and then we know the sequence might just be 2, 4, 6, 8, and then all the way down for all the even values because it's 2. And you can test different cases to verify if the conjecture holds, but at any point if you find a counterexample, for instance, if you find 9 inside the given sequence, then it will never be 2n because it doesn't apply. And therefore the conjecture is disproved in this case. But finding cases that match cannot mathematically prove a conjecture, only brings evidence to support, if not essentially proving it. If we're proving a countable infinite set of cases needed for a conjecture, such as proving all positive integers work for a certain conjecture, we can use mathematical induction. And I'll give you an example, because sort of in this case, just that there's so many, like there's just an infinite set, blah, and then let's n equals to infinite. Then there's no way you can look through all of them to find if all the cases match. So in proving the set of all positive integers, we usually do these two steps, which is, first, we need to show the conjecture is true for n equals to 1 is true. And after that, we need to show if it is true for a particular n equals to k, and then it is true for the next one. So n equals to k and n equals to k plus 1. We generally won't find an exact value for k because we need to generalize it based on the given circumstance, as we want to be more precise in mathematics. So let's start with an example. So prove that all n factorials is bigger than 2 to the power of n for positive integers n greater than 4. Try to pause the video and give it a little try. 5, 4, 3, 2, 1. Okay, so prove that n factorial is bigger than 2 to the power of n. And the solution is, we can do n equals to 4, because that's the very first one, n equals to 4. So what is 4 factorial? 4 times 3 times 2, which is 24. And what is 2 to the power of 4? That's just 16. So we know this certainly stands because 24 is bigger than 16. And assume that this is also true for n equals to k, because we're trying to prove it's true. So k factorial is bigger than 2 to the power of k. And now prove that for n equals to k plus 1 factorial is also bigger than 2 to the power of k plus 1. So k plus 1 factorial is bigger than 2 to the power of k plus 1. And what can you tell from these? Yes, you can tell 2k times 2 is the exact same as this. So we know that k plus 1 factorial is bigger than 2 to the power of k times 2. And then, which is just equals to 2 to the power of k plus 1. And then, okay, that was really bad here. So now we know k plus 1 factorial is equals to k plus 1 entire thing multiplied by k factorial, since we're just multiplying by the next term. And then after that, we know that k plus 1 multiplied by k is bigger than k plus 1 multiplied by 2 to the power of k. And how do we get this? Because when you assume that when n equals to k, k factorial is always bigger than 2k, 2 to the power of k, so it's going to be bigger than that because you're multiplying by a bigger number to the same value. So which is bigger than 2 times 2k, bigger than 2k plus 1. You see, now we know that k plus 1 factorial is bigger than that. So essentially what we're using is we're using the previous term to prove the next term. And the result is true for n equals to k, and it is true for n equals to k plus 1. So it is true for all positive integers, because we can just assign any constant value for k, and it would work. For integer cases, because we have to use integers in this case, else there is a chance that might be a fraction. And now we have another example, which is prove that for all positive integers n, the nth derivative of the function x multiplied by e to the power of ax is always equals to n multiplied by a to the power of n take away 1 eax plus a to the power of n times x e to the power of ax. Try to do this on your own for a real quick second, and then I'm gonna explain where a is a constant. Yeah, a equals to constant. And okay, let me just guide you quickly through. So for any 1, because we're of course going to start off with 1, and therefore we know that if that's just the first derivative, we're going to use the product rule, which is x multiplied by e to the power of ax. So how we do that is the derivative of this multiplied by that, and then the derivative of that multiplied by that. So essentially it's just derivative of x, which is 1. So e to the power of ax plus derivative of that, which is what is that? That comes down ax eax, and then does it match? That's 1, and then n take away 1, that's just 1. So it works because that's equals to 1, and which gives us that, and then that is equals to n, which is 1, and then I guess that. So we prove that for n equals to 1, the case stands. And then after that, we have to prove for n, which is n equals to another number where it is not 1, but then it also stands. So let's assume n is some integer bigger or equals to 1. Then we have the original formula, and then we have d, and I'm just going to quickly write it again. So, we're going to add 1 to it to prove the original formula. I think it's ax. Sorry, I wrote that very badly. Ax equals to a to the power of n take away 1, n a to the power of n take away 1 eax plus a to the power of n times x ax. Yes. So what we essentially do is we just derivative both sides by one more time. So we just derivative that, which just gives us, let's say, so essentially what we do here was dn and then plus 1, and then dx n plus 1, and then so when we do this, we got a derivative the other side too, because we're differentiating this again. So we know that's just equals to n multiplied by a take away 1, n take away 1 multiplied by a ax. Yep, I think so. And then plus a n times by e to the power of ax plus ax ax. Yep, so these two and these two differentiate two different stuff, and I use the product rule. And then let's see, which gives us, when we expand it, n a n, and then because we're multiplying by n, e a x plus a n, because we have this here again, and e a x plus a n plus 1 x e a x. And then that, because we have these two are of similar base, what we can do is, oh sorry, that's meant to be a power, sorry, I wrote it a bit too big. That's meant to be just n plus 1 multiplied by a n e a x plus a n plus 1 x e a x. And then because we're doing this for the term n plus 1, we can see it actually works because n is just equals to n plus 1 take away 1. And then n plus 1 is also here. So the case stands. And then through induction, we prove that this statement, where the derivative of x multiplied by e to the power of ax is always going to give us n times a to the power of n take away 1 multiplied by e to the power of ax plus a to the power of n times x e to the power of ax. And that's induction. Hope you learned something, and make sure to follow up next lesson. I'll try to upload more videos in the next few weeks or so because the exams are over, and good luck.